Let's start off with reviewing NAS and EAS. Do you guys remember what the acronyms stand for? Not a single two of you said the same thing. That was great. Yeah, I heard nucleophile in there, I heard aromatic, I heard substitution, and electrophilic. NAS can also be called SNAR, which resembles the naming convention that we use for SN1 and SN2, but explicitly describes it as aromatic nucleophilic substitution. Silly. It's silly because SN1 and SN2 describe the kinetics, first order, second order kinetics. Aromatic doesn't describe kinetics, it just describes the functional group. In this reaction, a nucleophile attacks an aryl halide. So the ring is substituted by a nucleophile. In EAS reactions, the ring attacks an electrophile. Jackie, don't worry, I haven't forgotten that we're still doing vocab review. So let's review what those words mean real quick. That's really cut off. Nucleophile? Nucleus loving. Donates electrons. Electrophile. Electron loving. You know, I won't lie, sometimes the definition donates electrons or accepts electrons comes across a little confusing. I think about in the first instances that we learn about nucleophiles and electrophiles in OChem 1, we get types of substitution reactions. I can see how hydroxide fits the definition of an electron donor, but then it kind of feels like carbon is donating electrons to the bromine as well. Or another way of saying this entire reagent is the electrophile, the carbon is the electrophilic, but doesn't it really feel like bromine is the one that's getting electrons, whereas carbon is just swapping how many it has? Sometimes these definitions don't make the best sense. You just have to get comfortable with it. All right. We have some limitations, complications on NAS and EAS. NAS reactions are promoted by electron withdrawing groups. When I say promoted, I think there's a better word, activated. Which literally means the activation barrier drops, so less energy is needed. Inhibited by electron donating groups. And EAS is almost the opposite, activated by electron donating groups, deactivated rather than inhibited by our electron withdrawing groups. Earlier in the semester, you guys ran the nitration of methyl benzoate. What type of reaction was that? Where's the aryl halide, Max? It's got to be electrophilic. Even if you're not confident, there's no halogen. So it can't be NAS. Now you can be confident. Nitration is always EAS. And we ran that reaction incredibly cold. We run that reaction cold because if we're not careful, the nitrated product gets nitrated. What reaction is that? NAS or EAS? Still EAS. Nitration is always EAS. But the carbonyl is an electron withdrawing group, so that deactivates the ring's ability to do EAS. The carbonyl and the nitro group are electron withdrawing groups, so they both have a compounding effect, deactivating the ring, making it harder for the ring to do this, and yet it still gets nitrated another time. If you don't keep your reaction at 0 degrees C or lower. So why is it that a doubly deactivated ring needs to be chilled on ice to make sure it doesn't react? What that means, if this is not a one-step mechanism, so I guess I can show the intermediate. If nitromethylbenzoate has this activation barrier, and this is less reactive than just benzene alone, then the activation barrier that benzene alone must have would look like this. It doesn't take a lot of energy to do this nitration. That's why we have to keep energy away from it as much as possible. This activation barrier is quite small, and that is an elevated activation barrier. It's even more deactivated than just benzene by itself. So benzene alone would require very little energy to be able to do this. Does the visualization help explain how these groups deactivate the ring relative to benzene? Now imagine that you weren't doing the nitration of benzene, but you were doing the nitration of toluene. How does toluene compare in its activation for EAS to benzene? It's more reactive. It's more activated. It counts as an electron donating group. So if this is how little energy benzene needs, then toluene would have an even lower activation barrier. It would take even less energy. You nitrate toluene once, and you get nitrotoluene, and then you nitrate it a second time. It still doesn't take much energy, and then you can nitrate it a third time, and you get big boom, trinitrotoluene, TNT. Doesn't take a lot of energy to make TNT because toluene itself is already quite activated towards the nitration process. But it does release a lot of energy when it goes boom. Cool. Okay. That's the background on it. Let's look a little bit at the resonance contributions in the mechanisms. True or false, you guys will have to draw a mechanism for NAS or EAS on the final. False, you don't have to draw it. True or false, there might be questions on the mechanism in the multiple choice section. Very true. So no drawing the mechanisms, but understanding the mechanisms, very important. Here was one of the mechanisms that I had you learn before the midterm, the bromination mechanism. That nitrogen and that oxygen both have lone pairs. And it's those lone pairs that can be donated into the ring. They themselves aren't going to act as nucleophiles, but they are still donating electrons to the ring to make the ring a better electron donor. So they are being the nucleophile by proxy. Which of these two groups donates its electrons better? Yeah, nitrogen shares better because less electronegative. It doesn't care for its own electrons quite as much. So let's show what happens when nitrogen shares its electrons. It's only allowed to share it with this carbon. That carbon just broke its octet. Not great. So in order to unbreak its octet, that carbon needs to break another bond. In order to accept a bond, it will have to break a bond. And the bond most easily broken is the pi bond. So we can show the pi bond breaking to the other carbon in the pi bond. We can see that this gives us a resonance form where nitrogen holds a positive charge and carbon holds a negative charge. Is that a very good resonance form? No, that kind of sucks. Maximum charges and wrong charge placement, inappropriate charge placement. But we can keep going. That negative charge that is now in the ring, the electrons that have been donated by the nitrogen, they move around that structure in predictable patterns. They have this 1-3 movement across pi bond regions. So there are specific atoms in the ring that end up ever having the negative charge. So when we look at the starting material, we shouldn't think of it as any carbon is equivalent to each other. What we should think of is that groups that are ortho and para to our strongest electron donor, those carbons have a resonance form where they hold a negative charge. Those carbons are better nucleophiles than any of the other carbons. So electron donors become ortho-para directors. Deactivators are meta-directors. Halogens blur the line. Halogens technically steal electron density from the ring, making it less nucleophilic, but they also stabilize the intermediate by donating electrons, so they support ortho-para positions. Halogens are the middle guy. So certain positions are more likely to act as a nucleophile, and when those positions do act as a nucleophile, the strongest electron donor is there to stabilize the carbocation that appears. It's able to or sorry, able to stabilize the cation that appears. It's able to maximize octets still. Electron withdrawing groups in NAS are just the opposite. Electron withdrawing groups pull electrons out of the ring and rotate this positive charge through the structure, orthopara to itself. So when considering where a nucleophile might attack a ring, we can look at where an electron withdrawing group puts the strongest partial positive. Only one of those bromines ever has a resonance form where there's a positive charge on the carbon. That makes one of those bromines more likely to be the one that is substituted. It makes one of those carbons more likely to be attacked. Okay, what other details on NAS and EAS should we refresh? Good question. The leaving group in NAS is always a halide. Do you guys feel confident on what your electron donating groups are and what your electron withdrawing groups are? Okay. Then let's, yeah.
Yeah, can you just go over like why are carbonyls withdrawing, but then like ethers?
Ester.
Yeah.
Yes, great question.
Well, ethers are donating, right? They get an OR.
Oh, yes. Well, esters can be electron donors or electron withdrawers. It just depends on how they're connected. Ooh, two esters, but very different effects. If I have an atom that has lone pairs connected to the ring, then that atom can donate the lone pair into the ring. If I have an atom connected to the ring that is also in a pi bond, then that atom can pull electrons out of the ring and push its pi bond. So it's about lone pairs and pi bonds. In fact, this would be a fun little resonance form to draw. Wow. Cool. Cool stuff. Oh, it's off camera. Bummer. Yeah, but then I have to bring this. Did that answer your question, Elliot?
Yeah.
Kind of highlights the difference on how the same group can have two different effects depending on how it's connected. The two kind of outliers when we're establishing donating groups and withdrawing groups the halogen and the alkyl group. The alkyl is considered an electron donor. Does it have lone pairs that it can donate? Definitely not. So why is it an electron donor? It has electron density that it can donate if the positive charge ends up on the carbon with an alkyl group. Unlike with the nitrogen and oxygen, which can share a lone pair, the alkyl group gets a positive charge on this carbon, and it just kind of shrouds the positive charge, but it doesn't actually satisfy or share electrons with the positive charge. So it is an electron donor, it just is not a strong electron donor. The halogen, does it have a pi bond that pulls electrons out? Definitely not. But it does have a strong dipole moment, a strongly polarizable atom pulls electron density towards itself rather than being able to share. The halogen actually has a lone pair that it can share in, but it's not considered an electron donor until the resonance form. If the halogen is ortho or para to where the electrophile has been attacked, then the halogen can share a lone pair to help stabilize the intermediate, lower the activation barrier, but it also raises the activation barrier by making the ring less nucleophilic. So the halogens are just slightly deactivated relative to benzene, and it's because of this destructive interference of pulling electrons away but stabilizing the intermediate. Hurtful and helpful, almost a wash in the end. Fun stuff. Okay, why don't you guys work on your multi-step synthesis problems, unless you have more on NAS and EAS you want to ask. Oh, yes, you may.
Is this like one?
Yes. Top one is long, so I gave you the middle. And then the others are, actually the top one I imagined was kind of the hardest. So I showed you how many steps I'm expecting and gave you the middle. The other ones are multiple steps, at least 3. No, at least 2. The others are at least 2 steps, but I didn't give you the cheat codes. Didn't tell you how many steps or any of the intermediates that'll be there. I'm going to upload these documents. Be careful back there, Killian. Oh, where can I upload this? I guess in the final module. Okay. Hello.
Can you let me into 298?
Yes.
156 didn't have any checkered tables.
Okay. All right. Are you guys okay for a couple of minutes? I'm going to go make more copies of this as well. How many didn't get this? 1, 2, 3.
Oh, wait, did you upload it though?
Yeah.
Okay.
Okay.
I have my reaction table that I put my blood, sweat, and tears into. I know what that is.
Unsaturated.
It can work,
No,
right?
no.
Cause this is an alpha,
There's
and I
no
would do it
There's
with
no carbonyl either.
NaOH.
Not a dicarbonate.
And the beta, and then you make the enol that has this on
Yeah.
it.
No double bond, no hydrox.
What was on
So
it?
we'll get, we'll get like a,
So we could get like an alkene and then just.
Oh, yeah. Oh, no, he wants it different. Cause I'm thinking like, wait,
No.
I think I just wanna
We could quote
die.
the,
No, I'm just,
hydroxide is Jolene's group.
no
right?
more.
So we
It
could just
sounds
do a
really
normal
nice.
aldol addition. And then just do a. Just do like a tag, like aromatic green, do it.
Oh, yeah, you're right. You should.
I don't know why
put
that
it on
wouldn't
here.
work.
The beta one that we learned last time. But the one that was on the unit test.
I didn't even know.
No.
What is the?
My phone died.
We can make this, it's just, this will have to be unsaturated,
No,
there'll be a double bond, so if you figure out a way to make it a double bond, then
okay. Right, so then I just added. Yeah, I just added, right?
Okay.
So you. But don't you have to have the equivalences of it? You haven't. Right, that would work, right? I guess it could.
organometallic, right?
Okay.
No.
And then from there.
Unsaturated.
I'm not even sure. Can you just start
So
with
just
that?
reacting when you make
Something else.
this area right
Cause I
here, then we
feel
can
like
use
I,
the
it can just be
organometallic to make a double bond with the metal.
Are you done now?
Because the OH makes this a double bond.
How do I not have a
And
pencil?
the organometallic will attack the double bond and make a metal.
Why is it impossible?
Oh, into that.
You're making an alkene.
Oh, no, it needs
with
heat
these are
too.
also conjoined, so
If not, it just makes an OH, it makes an addition reaction.
like this would be an aldehyde right here, and the bond is
Oh,
an
for
OH
sure.
reduced to an alkene.
Oh.
Then organometallic can attack the alkene.
Cause if not, it just puts an OH here.
Because you know what, for aldol addition, this will
Which
have
I'm
to
not
become
sure is a
double
bad
bond.
thing,
The, like, the needs to.
because can't OH, then isn't OH an electron?
I can show you that.
Sorry, I'm just gonna over to my left.
Just do an addition and then remove the alcohol. I mean, if we can remove the alcohol, yeah, but how would we get it back?
no, like with the, like
Oh, yeah. I'm
reactive
so done with that.
Right.
with something big, get an addition product here, like the intermediate would be like, like
Actually,
this would
I
basically
think it
be one
has
of
to
our
do with,
reagents.
I think this
And
actually
then,
is
I guess
supposed
that's
to be
not
an
our
addition.
step. I don't think it came across yet.
You wanna know what my
So, yeah,
boyfriend
maybe
said to me this morning?
the-
I got glue on my lashes, and this man is like,
Alcohol, I think.
sit down, and I was like, okay, and he just sat there
So
and
if
picked up
you
glue.
alcohol, the alkene, that template,
I was like,
we're trying to figure out.
I was like, I literally didn't even have the energy to find it, so I was just like, whatever. Yeah, he was like, I got you.
Oh, yes.
Thank you so much.
Yes. You want to?
Thank you, Josh.
You bet.
I appreciate it. Wait, okay, so
Yes, and if you have feedback on it, let me know.
it's great.
I know, but I'm sure it's not done. I'm going to try to redo my functional group table too.
Some of these I like swear I wasn't here. This.
It makes an.
Which one?
This guy.
What does he do?
Sodium amide is a strong base,
Okay.
And a good nucleophile for NAS. It acts as an electron donor, attacks the aryl halide.
The rest I think I know. That one I didn't know though.
I see.
All the ones with nitrogen, I feel like I struggle with.
There's a lot of weird little nitrogen groups, huh?
They're weird.
Yeah, no, the like H2 and 40. Oh, H2 and you could just make it.
I feel so smart. I already know the top one.
Why did this do nothing?
Would that like the?
Oh, I forgot to draw it.
Why did this
That's
do
right,
nothing?
Yours is, but hers isn't.
I forgot to draw it.
Jojo, have you learned nothing? Jojo.
Why did this do?
Like make a nerd and then add the alcohol and then add the nitro group.
You are wrong to think that. What you can do, Indigo, what you're suggesting is NAS. You're introducing a nucleophile, a Grignard, to attack the benzene carbon, but that means you need to have an aryl halide there. If you don't have an aryl halide, then you can't just attack.
Even once I get the CH2, CH3, how would I add the alcohol?
Oh,
A number of different ways you could do it. Alcohols form by alkene addition. Alcohols form by acyl addition. Alcohols form by reduction of carbonyls. So there are a lot of options.
what was I gonna say? Oh, for like both of these, does it matter like which one you use ever? Like, cause this one's in basic and this one's acidic.
No, it doesn't matter ever.
It just does the same thing.
Right. Katie, did you spot your mistake in your acylation? In your acylation step,
Oh, I forgot the.
right, you introduced a ketone,
Yeah.
which would have done nothing.
Yes.
Was this
I
it?
also forgot.
Yes,
to
it
draw
is.
half of it.
Yay!
Good job.
I kept missing this functional bit on my IR, and I literally couldn't figure it out until I crossed all the ones out.
Yeah, you did. Did you? I was worried you would even cross that one out and be confused like, I don't have a carbon that has 3 R groups. You know how it has that diagram of like what it's connected to?
Yeah.
And you don't, I mean, you do. But some people look at that and they're like, no, I don't have 3 different R groups and just 1 CH. But you got it. Great job. Yeah, it did. You can leave. You wanted to be excused? Bye. Hello?
Yeah, because there's a reaction that does two carbonyls together, right?
I will say, this is the only class I've ever had where like I can come in a bad mood and leave like in a bad mood.
That's really impressive.
It is,
And-
especially because it's okay.
And that's not a me thing, that's an us thing.
Yeah, it's a good group.
Mm-hmm. It do be a good group. Imagine if these guys weren't next to you the whole semester long. It would have been different. You know, you come into a one-on-one meeting with me in a bad mood, you might still leave in a bad mood.
That's not true.
Have-
I came in a very bad mood when you tried to teach me resonance, and I was like, I did 8 hours of lecture. I'm tired. I was like, you literally.
That was.
What is resonance? And I literally just said, electrons. He was like, yeah. Yeah, basically.
Yeah, that's valid.
And I was like,
What, can I put like anything I want on an enolate?
Whoa. What do you want to put on an enolate?
A ring. Like put the enolate and then like attach a ring.
Yeah,
Is that
so
allowed?
yeah,
Okay,
sounds allowed.
great.
An enolate is when you've got a nucleophilic alpha carbon.
I'm talking like, yeah, I'm talking like this. And then
That's an enolate, yeah.
this is the pH ring.
Totally. Now, alpha acts as a nucleophile, and at the end,
They switch.
no, they don't switch.
Oh, I mean like,
Well, that looks like switching, the woo. But they don't switch. When alpha attacks, you get a shared beta dicarbonyl.
oh my gosh.
The second one on the same location.
But,
Is that what you want?
Yeah, because then it's technically like,
Instead of it being in.
the way that I think of it is like this bond and this
I'm
bond
gonna
end
just
up like
also-
connecting.
Yes, that's exactly how you should think of it.
Come back to it.
They're, like,
So then
both
I should
a
have
bond.
1, 2,
we just add, like,
3,
on this
4,
one, an
5
OH
with the
on the
carbonyl, 6.
With the chain?
1, 2, 3,
that allowed?
6.
I don't think so.
Where did 4 and 5 go?
Great, 'cause then we could just-
What?
it would be.
This is, darn it. Oh, wait, how does that?
Right. You're in the right reaction type. You're trying to do conjugate addition. But conjugate addition with an enolate doesn't give the same product as conjugate addition with other types of reagents. Those are all conjugate addition. Oh no, the one that goes down is acyl addition. All the rest of them are conjugate addition. Conjugate on the right, conjugate on the left. What was your question?
Can I do this to form that?
You sure can.
Is there a way that I can attach a bromine here, direct it here, and then use NaOH?
Nope.
Okay, so is this step helpful?
No.
Okay,
No,
Oh, wait, why
maybe,
does
but
that not work?
probably not.
okay.
Okay, I have a question.
Why does what I do not, why does it, sorry?
Let me draw out what it makes.
Circle around.
Because that would be 1, 2, 3, 1, 2, 3, and then the ring. What?
That's what you're making. You make a shared beta dicarbonyl. Hi, Camille. Yes,
But we only need one carbon.
I'm listening.
Fluorination and bromination, like when you join an allyl,
Oh, great. Or is that acylate?
That's alkylation.
Alkylation. Can you add, like, hypothetically, an oxygen group to the end of the carbon chain and add it?
You can't have alcohols in the presence of a Grignard.
Stupid Grignards, okay.
Yeah. No, that's a good question. And you see why, right?
Is this legal? Yeah, can we add an ester?
Straight to jail.
Can we add a, he's like arrested.
Do you know what? I don't think so.
Okay, that's, but you can add
aldehyde or
Yeah,
ketone?
that's right.
Okay.
And you see that those are quite different
Yeah.
reagents, right? The ester, do you remember that in the acylation mechanism, the activated electrophile is this. Yeah, the chlorine bonds to aluminum, and then the chlorine falls off the carbon, and it leaves us with a carbocation, but that carbocation would more willingly accept electrons from the oxygen. Oops, so yeah, that's why it looked so wrong. Yeah, that was cringy. We form this. If you had an ester, I guess you have the possibility of also forming this instead. An OR group forms this. And to be honest, this is alkylated carbon dioxide. It's CO2 with an alkyl group. And I think it might fall off. But I have not seen it. And do you know what? I really don't like when people investigate chemical reactions that end up having no results or meaningless results. So they never publish it or talk about it because it wasn't meaningful data. Now I can't learn from it. I'm saying I've never seen somebody do a reaction with an ester acid halide, and it could be because it doesn't do anything. And rather than saying explicitly, don't do this with an ester acid halide, they just never mention it. When I was in graduate school, I did a lot of experiments that proved useless. And I wish I could have written a paper and said, guys, don't do this. It doesn't lead anywhere. But no one publishes a paper that says, I tried all this stuff and nothing worked. I agree, they should. If you have any questions that you want to add to the list, we did our NAS EAS review earlier.
Okay, oh, it's a video on that.
And a couple of we defined nucleophile, electrophile again. So we're just doing this. Some students last week had asked for a list of all reagents. So I thought I'd see what it looks like.
Okay.
I'm not sure the best way to organize them. So this is what they look like alphabetized. This is what they look like kind of broken into categories, but these categories are a bit arbitrary. So if you have feedback on this, I'd be super interested to hear. Okay.
Oh, would it not put an OH in the wrong spot? Oh, no, it wouldn't. If we made this a whatever.
My whiteout isn't very happy right now.
Wow. I didn't know that could come apart even.
The more you know, right?
Yeah.
I don't know what's wrong with it though. Oh. I had one come apart. I never got back together.
Mm.
Oh, perfect. So should we just send these? Insane to think that you should make this into an ester to then turn it into that. Oh my gosh.
You do not need to turn it into an ester. No. But if you were, it wouldn't be by introducing an ester.
But isn't there like an alcohol to ester reaction? Literally, that's
There's a reaction that takes ester to an aldehyde. But there is not a reaction that takes aldehyde directly to ester. What you know you want to do eventually is form this bond, right?
Yeah, and it takes an extra carbon to do it.
No, it wasn't supposed to. I'm sorry.
It's okay.
It would though, right? Like I'm not.
Yeah, you're so right. I messed up. Messed up. This is not meant to be a 6-membered ring. It should be a 5-membered ring. Indigo pointed out that there's an extra carbon that's needed by the end of that last step, and that is not what I was going for. I wasn't going for an extra carbon needed, so I screwed up when I made that structure.
The exact same with our synthesis, so.
Yep. Yep, that's what I was going for.
Yay!
Thanks for pointing that out, Indigo. I would not have noticed it. Do you know sometimes I make those mistakes on my exams? Just small little mistakes that a student that doesn't know what they're looking at would just glance right over and get the question right. But students that know what they're looking at, overthink it, think about it critically, and then don't know how to answer it because there's no right, it doesn't make any sense because they understand the mistake. Yeah, you would have.
Can you help me remember how this works though? Because I get it because I saw it on her cheat sheet, but I can't remember like why.
Sure, I'll show it.
So, I'm wondering if, because I know like the Grignard you can't have an alcohol, so I'm wondering, can you add the bromine, like if I was going to use like this Br2 and HV or light,
Yeah.
would that still attach here? Well, like it does in this mechanism? I'm looking at my own notes and I took pictures of them. Like if I did Br2 and light here, would this then?
I think it would have a better chance of attaching here. I actually don't know how the alcohol interferes with the benzylic position's reactivity.
Okay.
So I will tell you that was not the intended. That was not the intended plan.
Okay.
Yep.
Back to the drawing board.
Back to the drawing board. Well, there is a difference between what you have and what she has. Hers has 1, 2. First, we add this, then we do an aqueous workup. Good.
Sorry, I'm trying to remember what I'm doing. Okay.
I'll come back.
Okay. I still don't know what's going on.
1 second, James. I'm going to answer Yoon first. I'll be right there.
Actually, I think I can get a 6 rings, but I'm not sure correct or not. So forming this first, and then using this as alpha and attack.
Mm-hmm.
So 1, 2, 3, 4, 5. This 6.
Yeah.
Kind of like.
Yeah. Although,
5.
just because I intended for you to do it in a certain number of steps, I think the way that you're doing it would be 1 step longer. And it does give you that 6 carbon, which means you're kind of correcting for my mistake. And that works good. It's just not the route that I was planning. I like the way that you've done it. I agree that this would work. Mm-hmm.
Okay.
It is more common that we use acid chlorides than acid bromides,
Okay.
but I don't need you to change it. That would be full points. It works in a very similar way. I just want you to know you'll maybe never see it.
Okay.
Yes. What's up?
Oh, Bob, we were working on the 6 member.
Ah.
I don't know, this is.
Yeah, the 5-member
This is
ring.
gone. Yeah, you'll show it. I don't know how to do that step.
I see. So to get from here to something to get to here.
Yeah, I was going for a 6-membered, so I was thinking we would add
Yeah.
like an aldehyde, and then, you added a ketone, and then did that, but.
Oh, that's right. Yours would add too many carbons.
Too many carbons. Yeah, I just felt.
That's right.
Yeah, it's just 6,
And
7.
and yours produces no nucleophilic carbon. If you add an aldehyde, neither of the aldehydes
We'll have carbon.
have an alpha carbon that can attack. Go for the 5-membered ring. Get rid of that carbon. The benzylic carbon should be a benzylic alcohol, and then you might be able to solve it. Sorry. Oh man, it's such a silly mistake.
Can we use this guy for this one?
Yeah, you could. I thought you did earlier.
I
Isn't
used
that-
a different organo.
Oh. What do you want to use now?
I'm just saying this gave me this nice oxygen. Oh,
Yeah, that's exactly what you did before. RM is just generic
No, I
organometallic.
think I used CRMG, or I used,
Yeah,
Yeah, that's
other.
an organometallic.
yeah, just, yeah.
RM is not an organometallic. It's the concept of an organometallic.
Okay.
Is that right? Is that how that works?
That's what you. Oh yes. You forgot the subscript 2 after the phenyl.
Why is there there has to be two?
Yeah, the copper will bond to 2 groups, but only use one of them.
And so does the CULI, like, does it make the enolate?
It would work, it would be another, yeah, it would work.
Like that? How it was like.
No, there is no enolate.
But we did that.
Oh, when it attacks,
Yeah.
yeah. And that's why we have to
And
protonate.
so the CULI makes it an enolate, right?
Yeah, it attacks the conjugate position.
Okay.
It forms an enolate byproduct that then gets protonated. Yeah.
Okay.
James, what you got?
So, for this first part, would like something like would this work or like NaOH?
Yes, but NaOH with 2 equivalences of this forms an alpha beta or a beta hydroxy carbonyl and then an alpha beta unsaturated. Perfect.
So so from here I can still work towards this, right? Okay.
This is exactly what I was hoping you would find. Yep.
Fine, yeah.
I would look to add something else.
Yeah.
I don't think that we can have alcohols on the carbon chain when we do alkylation. Even still, this is an electron donating group and it won't direct meta.
Right. Yeah, I have a, yeah. That was just kind of, I'll try it. Wait, so just these arrows is not, so this is not a one-step thing.
That's right.
Yeah, fair enough.
Not a one step.
Right, 'cause that's something that.
Okay. Peyton, can I show you the arrow pushing now?
Yeah, can I, to break can you use MCPA? Am I crazy?
MCPBA takes a ketone to an ester. Isn't that wild? And it takes an alkene to an epoxide. You know?
What's an epoxide? I can't remember.
An epoxide.
Yeah?
Right.
With the O.
You're so
There
right.
you go.
Oh.
Illuminati. Illuminati confirmed.
Anyways, yeah, please show me things.
Yeah, so an intermediate that we get here, I'm going to abbreviate part of the structure.
Okay.
But the intermediate we get is this. These electrons are owned by carbon because magnesium is less electronegative than carbon. So carbon takes the electrons and attacks the carbonyl.
Okay.
That is what allows us, in this case, it allows us to form our ring.
And then they're just
But
like, okay, cool.
if they're not connected, right? Like if these are not part of the same molecule, well, you've just combined 2 molecules. Acyl addition. Do you want any hints?
No, I don't think
Okay.
so.
Not yet.
Not yet.
No, multi-step still, but I'm just pulling off the guardrails.
To make it close in on itself.
First, I guess, does those steps.
So what if we just add an S?
Do you use like the aspartate? Okay. The OH with the double bond, and then use, or would this just put that back as a carbon?
Well, I'm not sure what this would do. This is not a... Sure, yeah, it would deprotonate, but that would just undo your step.
How do I move that double bond into the ring, I guess? Or could it, or like,
Well, the question is, how do I get a carbon in a chain to bond to a carbon on the aromatic ring. We know about ways to get things to bond to the aromatic ring. Nucleophilic substitution, nucleophilic aromatic substitution, NAS, or electrophilic aromatic substitution. I can either have my ring attack that carbon, or I could have my carbon attack the ring.
So in this case, your carbon's attacking the ring, right?
Maybe.
I guess I don't get like how you would make the carbon go one way or another to like how do you give it the not like the charge, but the electrons.
Well, I think literally what you're describing would be reduce it, give it electrons.
But then that'd just be this piece.
Well, I mean like reduce the carbon on the ring, give it more electrons. Another way that we make carbon-carbon bonds, we can do it by NAS and we can do it by EAS, but we can also make carbon-carbon bonds by acyl addition with organometallics. So if I could make an organometallic, I've already got an acyl group.
But how would the organometallic, I guess, connect them? Isn't it just sort of like attach a chain, not necessarily just form a bond between two already existing pieces?
Attach a chain means form a bond between two already existing pieces. Who cares if those existing pieces are also connected to each other or if they're connected to other things? The difference is if I have an organometallic attack an acyl group, I now get a longer chain. If I have an organometallic attack an acyl group on the same chain, now I get a ring.
So would it just be like the like Mg, I guess? But then don't you still need like the MgBr?
You would need a bromine for Mg to turn into a Grignard. Where's your bromine?
So would you just have it be MgBr or?
MgBr
I don't
doesn't exist. MgBr doesn't exist and wouldn't do anything. It'd be like saying sprinkle salt on this. So I'll need to get the bromine on first, and then I can introduce the Mg. You showed how to put a Br here, but this doesn't work.
Yeah.
HBr works
Break the double bond, right?
works with alkene double bonds, but aromatic double bonds aren't like alkenes. So if we want to put this on, alphabetized, so I'm looking for my halogens, what I need is,
Yeah, no, I think you can just do like.
oh, I guess I specified the halogens themselves. I need Br2 and FeBr3, or I could use Cl2 and AlCl3, because it doesn't need to be a bromine to become a Grignard. It can be a chlorine too. So if I want to put a halogen onto a ring, I need halogen and catalyst.
Yeah, I think that's what it's going for.
I'm wondering if we could also use
Because I'm assuming, I haven't finished this one. This step is just adding this piece, right?
The first step
Yeah.
and then somehow that
doesn't involve this,
to OH in the last step.
not all at once. What I want you to see here is that you have a carbonyl, and your carbonyl is conserved, but off of its alpha position, I get this new chain, and off of the beta on that new chain is another thing. So this is a group that has been added to the beta position, and the beta position itself is new. So this is from newer stuff. This is from Unit 5.
But this is not.
Yeah, this goes back to Unit 2 with aromatics. Unit 2 and Unit 3. Yeah.
Thank you.
You're welcome. Oh, I'm so old. That was hard to.
With what you're thinking,
I'll put the ester right here.
Yeah. I need to hang it.
No, no, no.
I
no,
do.
No.
For this one?
Yeah.
So we're thinking we have to make an ester.
We're looking at our
Close in on
aldehyde
itself.
page.
You have the answer, right? No? Oh, they have the answer.
We're looking at our aldehyde reactions, 'cause that's what
Right,
we have.
would that be like the right idea, is get the ester to close in on itself? Like,
Would this be the last reagent, potentially?
No.
is it not making an ester?
That's not an ester, that's an alcohol.
What?
That's an alcohol up there.
Yeah, I know. Well, I'm saying, no, for this one, do we need to get this to an ester so it'll close in on itself?
I don't know how an ester would attack the ring.
What about an epoxide?
An epoxide can be attacked, but then you would need to make the ring an attacker. And remember, epoxides create vicinal products.
Oh, yeah.
They create two new groups at two different positions.
Okay, yeah, so that would be helpful.
So you're saying that whatever is closing in needs to attack that?
Well, your carbonyl is electrophilic, so it is hard to make the carbonyl carbon nucleophilic. It's easier to attack the carbonyl carbon.
So it would be for attacking from this way?
That's a more likely way. So, formation of carbon-carbon bonds coupled with the formation of an alcohol. You could actually look.
No, we did that.
Yeah, we did. We've done that. Yes, sir.
Could I do an organometallic to attach benzoin?
Well, too strong of an organometallic will attack the carbonyl carbon. So I actually need a weaker organometallic. Do you remember which of our organometallics is weaker?
So, is lithium organometallic as well? Or?
That is just as strong as the Grignard.
So a cuprate?
A cuprate is weaker.
Oh, shit, okay.
And what you're doing is Michael addition. And back in our Michael addition unit somewhere,
Yeah.
I feel like it might have been,
It's like, was it this big?
yeah,
Like, yeah, it's like.
on the front?
Oh,
No.
That was actually a sheet of paper. Where is it? Right, that's the alpha.
Yeah, I gave you guys a lot of paper this semester.
Yeah, no. Some of it's also like. I think I know what you're talking about, yeah.
The Michael addition involves an enolate, but this is a conjugate addition with a cuprate. Good.
I think the socket ones.
Yeah?
Yeah. This one should be like this, creates
Yep.
and then you need the organic.
Perfect. That's what I was going for.
Can you do this? Can you just add alcohol, or does it have to be like a ketone there and then have another step?
Yeah, I don't think you can do it with an alcohol. Also, I need to do better at teaching this in the semester, so I'm avoiding making this an issue on the final.
What is the issue?
Alkylation and acylation of rings doesn't work when you've got electron withdrawing groups on the ring.
Will it work as NAS? Like if we had a halide before and then do that?
Yeah. You can do nitration and sulfonation and bromination and chlorination with electron withdrawing groups on, but you can't do alkylation or acylation with electron withdrawing groups on.
Okay.
Or I think I should say with just electron withdrawing
So you
groups.
can make NAS by just bromating it first?
Yeah, you could.
Okay.
And then it leaves.
How are you doing?
I don't know. Just evaluate.
Yep, that was my plan down here. This gives the opposite regeochemistry. Yeah, this one will give you a less substituted alcohol. Great. That's exactly what I was hoping you would do. See, what you've tried to do here is create a Grignard attached to a carbonyl. But those two things are like trying to have an acid in a base.
Okay.
They won't exist.
Yeah.
They won't exist with each other. So I'm going to have you try to find another way to get that carbon in and make the groups.
Okay.
That's great. Yep. And I didn't sign off on this one at all, did I? Okay. You know what? That is a good way of doing it. Not the way that I was planning. My suggestion, or my route was 2 equivalences of this to make this compound.
Okay.
This is your conjugated carbonyl, and then introduced phenyl cuprate for conjugate addition.
Okay.
Attacks the beta position, and then that's great.
Okay, perfect.
Good job.
Thank you.
Sometimes R is just a placeholder, and you can make it whatever you want.
So
But
could-
usually it means consider a carbon chain
do I have to consider?
or a hydrogen. Especially here where we were doing aldehydes and ketones. R for sure could be a hydrogen or a carbon.
In this case, so
Yeah.
that would be,
Yep.
is this right then? If I use this reagent here?
Well, it looks like you're going to lose a carbon out there.
Okay, well,
Do you agree?
I figured out
You're like
I know.
this close. I
what they did,
don't think you want that alcohol.
I don't,
but I don't understand if
but I want the,
if you add an organometallic, how does that attack here and remove that?
Ah, you're not adding an organometallic. You're going to create an organometallic.
Oh, I know what you're talking about. Like this wrinkle.
That's adding an organometallic. That would have,
I don't even remember when we talked about organometallics.
well, that would attack this carbon, and it would create an alcohol, acyl addition. You would have to oxidize the alcohol if you wanted a ketone again.
What chapter was organometallics?
Unit 3,
But would it add this methyl group
chapter,
here?
section 18 maybe? 17? What did you say?
Would it add that methyl group there?
It would add the methyl group and create an alcohol.
Oh,
Yep.
it is on here. Okay, it's this.
Which I want.
You do, but you don't want to make a carbon-carbon bond with a methyl. You don't actually want to add a carbon at all. That carbon up here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Can I ask you another
Ah, I see what you're getting at.
So, if we add just elemental magnesium, right? That was like
Yeah.
MG0 plus.
Yep.
So it'll
M-
remove
MZ.
this MG0.
MG
Zero.
0
Oh, I said plus.
plus.
And MG0. I was thinking like the dash through it.
You know calculus when they're like, it approaches 0 from the positive, which is different than it approaches 0 from the negative. And oh,
I know what you're talking
and that's how it felt when you said MG0 positive as opposed to MG0 negative.
But so, how does that work though? So if you add the elemental, like,
It creates a Grignard
oh, which
at the
then will
organometallic
attack
position.
That,
As soon as that forms,
then that'll attack and it'll go here since there's a negative, or like they took it from there. And then, because that has to become the OH, can you do H3O plus after?
an aqueous workup. Acyl addition needs an aqueous workup.
is this step right now?
Good.
Yeah?
Much better.
Oh, beautiful.
Because that's going to give you an alcohol where you want.
For this one too?
Mm-hmm.
Okay.
And it'll put an alcohol where you want the carbonyl to be.
Oh.
Your synthesis worked, just not to get the product we had.
Yeah,
I'll take one.
Do these look okay? And also, are we on the right track over here?
Yes,
Soul edition and then something.
but you could go directly to here.
Oh, I could.
Absolutely. And then
Probably in my alkenes, I probably should look a little harder.
this is an orthopara director. Yeah? Meta director, ortho-para director.
Dang, so I gotta keep it. And then add it. So just switch those two?
Good. Yeah, just like she did.
Is that right or wrong?
Yours is good.
Oh, okay.
I did the bottom one.
I think you got too many carbons here. Tertiary, secondary, primary, tertiary, primary.
That was the H3.
Can't have an organometallic in the presence of an alcohol. Is that an organ? Oh, you're introducing an organometallic. But organometallics don't exist in the presence of alcohol. They'll just kill the alcohol, deprotonate the alcohol. How many bags of these have you gone through this semester?
Just bought a giant box.
So same box
Yeah, same box. All
from
semester.
fall?
No, new one. It's spring. And then I'll get another one for summer.
Sure. Same deal with Andy here. This is a meta director.
Yeah, I gotta switch them.
That's an orthopara. Okay. How you doing, Camille? Not a lot of there's not a lot to go off of. So
I was like thinking you do the like beta hydrogen thing, and then
Good.
you could do like a Michael addition.
yes.
You can.
Mm-hmm.
That is the right.
Well, Michael is when you attack with an enolate. Michael is a type of conjugate addition.
Oh, okay.
If you're not using an enolate, then we call it conjugated addition.
So I can just do that.
Totally.
It doesn't have to be a double bond there. 'Cause I was
You
thinking I
do,
have to
you
do a
do.
double bond.
You do
Okay.
need a double bond there first, which means that
Okay.
you should run aldol condensation.
Okay, no, I was on the right track.
You're
I just
absolutely on the right track.
myself out of it.
Love to see these, by the way.
Oh, thank you.
These are great.
Yeah, I forgot my ones post midterm.
Oh, bummer.
I know, so I just have the old ones.
Wow. We got 20 minutes left. Did you know that? Is that real? Oh. Hey, Brett, how you doing? Oh, I thought everybody was going to come visit today. I was hoping I could get him in here to help you guys.
Sorry, you mentioned the nuclear reactions. That's what this is.
Yeah.
Does this just, the crossed aldol reaction, is it just combining these, or or do you need like an NaOH type of?
You do need a base.
It's just a base though, right?
Yep.
So for over here,
Yeah.
could you use like NaOH with that piece to combine it to that?
Yeah, is this 2-butanone? Or is it propanal?
It's 4, so it's bute, right? Bute is 4.
Yeah, and it's a ketone? Because that then is going to keep another carbon here.
Well,
But that won't quite agree with our carbon chains.
because this, if I just did a ketone, it just creates that double band off the alcohol and it drops.
Right.
That wouldn't be enough carbon.
Actually, so the crossed aldol is when you have two different types of carbonyls coming together, and both of them can be the nucleophile and the electrophile. So here's the crossed aldol where B reacts with B. Here's the crossed aldol where B reacts with A. Here's the crossed aldol where A reacts with A. And here's the crossed aldol where A reacts with B. So they are all different combinations of these two. If you look at your carbon chain, 1, 2, 3, 4, butanal, and 1, 2, 3, 4 connected at that primary carbon,
You just use 2 aldehydes.
two butanals. Yep.
And then
I know that is tricky, but I didn't say 2 equivalences here, but you can use 2 equivalences.
put NaOH.
You put NaOH, and half of this is going to react with the other half of it.
If you did still put that additionally, would you lose any points?
No, not at all.
And then, so
So I don't think that's right. You can ignore that.
Okay.
But then could you skip from this piece use like BR?
This is great. But this should be first, then second. We don't want to add the acid right away. Do you remember in lab when you made the Grignard and you had it attack a carbonyl? You didn't do that with acid in the flask. That's how you're phrasing it without the 1 and 2.
Okay. And then does this work at all? Am I insane?
You're not insane, but this is an orthopara director. It's not an electron withdrawing group, which means it's not going to direct meta.
Wait, but I thought electron donating was orthopara, right?
That's right. This is orthopara.
This orthopara.
No, this is an electron withdrawing group, not an electron donating group. So either we get this group on first, or this group starts as something else. What you have suggested here is NAS, but you're using a Grignard that has an alcohol in the structure, and Grignards and alcohols can't exist at the same time. So you will need to get this group on by a different means anyways, or make this group sometime later by different means.
So, because carbon-carbon bonds aren't really donating or withdrawing, I feel like.
Yeah, you're not wrong, but
How do they direct it?
but the alkyl group is still considered an electron donor because it has just an electron cloud that can be pulled by other groups. Boom goes the dynamite.
We gave up on this second one.
Really?
We were close. We thought about turning to carboxylic acid, but then that wouldn't work.
No, I wouldn't have done an acid.
I created this one, but I don't know whether it works or not. Probably works.
Yeah, you could do that.
Aldehyde. Yeah, because they thought it kind of like not stable.
Mm-hmm.
So
You can use the green with the aldehyde?
You can use a Grignard with an aldehyde.
Oh, I thought you could because they attack carbonyl, so you can't have a carbonyl on the Grignard.
Well, that's what I'm saying. He introduced a Grignard and an aldehyde and had them react.
It attacks the carbonyl, which is what we want, right?
Okay.
So you can't have a carbonyl on the structure if you want to introduce a Grignard somewhere
We could
else.
just do Mg and then like have the aldehyde come over. Okay.
Yep.
So this will like hang out because I thought you couldn't like have in like a two-step like have a Grignard just like. in
You
solution.
did that.
Really unstable. Oh, just as long as there's no water.
Just as long as there's no water or anything acidic or anything electrophilic.
Okay. So they are unstable. They're not like.
And you remember in lab that you were making a Grignard out of bromobenzene, which is an electrophile itself. So if you added in the magnesium in lab, but you only added like half of what you needed relative to the bromobenzene, then you end up with leftover bromobenzene, and they react each other in solution. They react each other. That was really great English. And you get biphenyl. So you do have to be careful about how you prepare a Grignard, but you can definitely prepare a Grignard safely. This is actually why we didn't have all of the bromobenzene in the reaction flask and then just add all the magnesium, because as it forms, it's going to find unreacted bromobenzene that hasn't formed yet and react with it. So we dripped the bromobenzene in to give it less of a chance of it reacting. It's definitely still a non-zero chance that some will react. Oh, too many carbons.
That's what I said.
Yeah, you lost a carbon there.
Okay, can you please tell me the answer?
Mm-hmm. Or a hint.
The answer.
A hint for the
Answer.
middle left, middle right.
Yes. I really want
before we leave.
Yeah, should I start going through them now?
Please.
Yeah.
Either that or just like if you could tell me.
Okay, I'll start with the one on top because most of you have gotten this already. The plan was to start with an aldol condensation. And I know you could also use H3O+. I know that I didn't put 2x in front, but you are using one half of the starting material to attack the other half of the starting material. That gives us a conjugated carbonyl. I'm not doing Michael addition because Michael addition is when an enolate attacks. Haha, sucks to be Michael. I'm doing conjugate addition. Yeah, the word just really escapes me. And conjugate addition is when I have any nucleophile attack. Michael addition is when the nucleophile is an enolate. I don't want an enolate to attack because I don't want a shared beta dicarbonyl. I just want one carbonyl. So I'm using a cuprate because it's a moderate nucleophile. Then I want to form a carbon-carbon bond. A follow-up of H3O+. Thank you. I'm starting to see more and more why a lot of professors say just skip the aqueous workups because they're all over the place and they're tedious, but it's reality, so I'm glad you reminded me. What we're trying to do next is make a 5-membered ring, and this is the ring that we're trying to make. Now, the carbonyl carbon is already electrophilic, so that would be a great spot to have a nucleophile attack. That means carbon 5 should become nucleophilic and attack carbon 1. Carbon 5 could attack carbon 1 if carbon 1 was an acid halide. Now my ring could just do intramolecular EAS. But that would be acylation with the use of a catalyst, AlCl3. That'd be intramolecular acylation, and I don't want an acyl group. I want an alcohol. I want to do acyl addition. Acyl addition leaves me with an alcohol. So I'll introduce a halogen, which is directed by the only substituent to the ortho position. And then I introduce magnesium to make a Grignard. As soon as that Grignard forms, it reacts with the carbonyl nearby, does acyl addition, and then I just wrap that up with an aqueous workup to get my alcohol. That was a long one and fairly challenging, but I was proud to see a lot of you found the conjugate addition step. You were looking for that conjugate addition. All right, here, there was a complication in what I had proposed for you, but a number of you found ways around this. Something that I'm not testing you on the final is recognizing that you cannot alkylate when you have a nitro group on. A lot of you tried putting the nitro group first, meta director, and then putting on the alkyl group. The way that I had envisioned this was to first do acylation and create an acyl group that is a meta director, and then run nitration directed meta by the, oops, that's not meta, directed meta by the acyl group, and then reduction. We could do LAH, we could do NABH4. If we can do NABH4, then of course we could do LAH. Another route, can you hold it? Another route was to nitrate first. This is what I saw you guys do, but it wasn't what my plan was. After nitrating, chlorinate, because the nitro group will direct the chlorine. meta to itself, and then do a Grignard attack. I'm just going to show this as one step. Make a Grignard out of that position and attack an aldehyde to create a secondary alcohol. Lily?
So if we did switch the,
If you switched acylation and nitration, technically a nitrated benzene really struggles to do acylation. It requires a lot of energy. They say it doesn't work. I don't know because I've never tried myself physically in a lab. And I always forget about that when I'm teaching, so I just try to avoid scenarios where that ever comes up. Some textbooks don't even mention it, you know? So, wrong? Yeah, I guess. But like on the right track and appropriate for what I would have expected on the exam? Yes. As you might say, good enough. Okay, the one on the middle right, this one has been getting you guys a lot. Are you ready for the solution? My plan was to use a Wittig reaction here, because I know you guys haven't seen the Wittig reaction a lot, because I sometimes just forget that exists. So, what we have in the final product is a vicinal diol. And vicinal diols can be made from alkenes using osmate. I'm not yet sure what the tert-butyl peroxide and tert-butanol do in the reaction other than being sources of hydrogen. And I know this looks like a 3. I see it even now. It looks like O3O4. It's OSO4. That is the element osmium. How could I draw my S different so it...
I think it's just me.
That looks like an ampersand. No, I say it every time I put it on the board because it looks like the way I do my 5s. So how do I make an alkene out of a carbonyl? That is the Wittig reaction. I can synthesize an alkene, carbon-carbon bond, by introducing a carbon double bonded to a phosphorus. Neat.
Can you explain how that last step works?
The carbons are not adding up in my brain.
Yeah, in fact, I can show the mechanism if you'd like. What's more electronegative, carbon or phosphorus? Carbon. Isn't that surprising? Carbon is more electronegative than phosphorus. So when we move our arrows here, they move by electronegativity. Oxygen takes the electrons from the double bond, attacks phosphorus. Carbon takes the double bond from phosphorus and attacks carbon. I love a good four-membered ring intermediate. That's how we form the carbon-carbon bond. The ylid attacks the carbonyl. The ylid carbon attacks the carbonyl carbon. And we form the alkene by essentially repeating that bond movement. The CO single bond breaks and the CP single bond breaks. And we're left with an alkene. So the Wittig reaction is an alkene metathesis, or an alkene synthesis reaction. Take a carbonyl, well, take an aldehyde or ketone. I don't know that this works quite as well with carboxylic acids, esters, or amides. Those, of course, are less reactive carbonyls. Take an aldehyde or ketone and make it an alkene. That was my plan. Some of you had some interesting ideas, and Here's a route that could have worked, but I don't think anybody got to this. Acyl addition with one extra carbon to give an alcohol. Turn that alcohol into a better leaving group, because alcohols are hard to control their leaving. But now that I have a better leaving group, I can control the regiochemistry. Introduce tert butoxide to give me a less substituted alkene. And then do the OSO4 to give the diol. That would have been, in my opinion, the only other feasible route. Either way, you've got to get to that alkene to make that diol easily. Okay. The one on the bottom left. Taking an alcohol and an amide and making an amide. This might feel similar to one of your homework problems. The homework problem, though, I think had a carboxylic acid and an amide, and then made a different amide. Obviously, we need the carbonyl on the bottom to disappear. That needs to stop being a carbonyl, and we can do that by reducing the amide. Reduction with LAH takes an amide down to an amine. All of the other carbonyl groups get reduced down to an alcohol, but the amide gets reduced down to an amine. Then I can oxidize the alcohol to become a carboxylic acid. And now that I have an alcohol and an amine, I can synthesize an amide. DCC is the dehydrating reagent. You could also have made the carboxylic acid into an acid halide and then reacted it with the amine. Yeah, that I think is probably the only route. Okay, and I had one last synthesis. I don't know where it went. I guess I never wrote it up here. Taking an alkene and making a hydrazone. So the hydrazone is formed by a hydrazine in acid reacting with a carbonyl. The carbonyl could be formed by an alcohol being oxidized, and the alcohol can be formed. I know some of you tried using hydroboration oxidation, but that would have given you a less substituted alcohol. Some of you did oxymercuration reduction, which is fine if you want to work with mercury. If you want to avoid working with mercury, acid and water. Yeah.
Still the previous one, the arsenic oxide one?
Yeah.
Why is kind of like OH and another one kind of like methyl OH?
Tell me again.
It's just a diol, right?
This is it's a vicinal diol.
Yeah, but it's CH3OH, right? That's kind of like.
Here
Yeah.
is CH2OH.
CH2OH. So we just have a OH, right?
Yeah. I'm not understanding the question.
I was confused too because it's the carbon-carbon double bond that everyone's thinking that it's gonna split, but it's not because there's only one carbon there.
Yeah, I see.
Okay. Yeah, carbon 1, carbon 2, carbon 1, carbon 2. The alkene goes to a vicinal diol. A challenging one for sure.
Because you use chromic acid as well as PCC.
Here. Yes. Chromic acid would have worked fine. It's been a great semester, guys. Thank you for all your hard work, all your engagement.
Have you written the test yet?
No.
Okay, well, can you tell us what you think will be on there?
Yeah,
You know what I mean? I'm not.
use
Like, what should I focus on studying? Everything's gonna say everything. Girl!
Did you notice how this review had everything? You wanted multi-step synthesis review, so I gave it to you.
Thank you. Can I ask you a question about when we're like reacting like alpha carbons and stuff?
Mm-hmm.
So it's like.
Do you guys need a picture of this at all? Can I erase it?
Do you guys have Instagram?
Yes, tell me.
I feel like I am so. I want to know because it's like sometimes something will have two alpha carbons, right?
Yeah.
On the left and on the right.
Yeah.
How do you know which one would react? Or
So-
consider the alpha carbon? Like, is it substitution or like?
First of all, only ketones have 2 alpha carbons.
Yes.
Aldehydes and esters only ever have 1.
Yeah, but so if it is a ketone, there are two.
If those carbons are of different substitution, oh, I need to talk to you too. If those carbons are of different substitution, different bases have a different preference. Big bulky base goes for a less substituted position. Small base,
Didn't we kind of talk about this?
thermodynamic and kinetic. And by we kind of talked about it, like, yeah, we talked about it.
Okay.
we drew the map.
Yeah, and it was so. Well, because there was one that it was like, oh, it attacks more or less substituted. So.
Right.